Across the unlit frontier between stars where silence grows ancient and distances defy imagination, a solitary mass drifts through the abyss. It does not shine, nor does it carry the warmth of any nearby sun. It is a relic of a place older than the planets that orbit our familiar star, a wanderer that has travelled so long and so far that even the galaxies themselves seem young beside it. In the long history of interstellar travellers, most pass unnoticed, mute stones swept along by the gravitational tides of the cosmos. But this one moves with a different gravity, a subtler weight, as though it carries not merely its own ancient matter, but an omen, a whisper from the universe's more violent past. Astronomers will one day name it 3i Atlas, marking it as only the third confirmed interstellar object ever to cross into the solar system. Yet long before any telescope glimpses its faint glint, the comet has already drifted past the realm of frozen hydrogen clouds and lonely brown dwarfs. It has crossed between spiral arms and skirted regions of dark matter invisible to the human eye. It has endured extremes of cold and emptiness that would turn any earthly material brittle, but the comet remains intact, a hardened survivor of ancient catastrophes. As it nears the sun's distant sphere of influence, no human being feels its presence. No satellite detects its passage. No early warning sensors yet know its name. But the universe feels it in the way gravity shifts when a new body enters the ancient dance of planets and light. The darkness around the object vibrates with the faint hum of motion, silent but constant, like a great pendulum finally swinging into view. If one could hover near it, they would see not a smooth sphere like Earth's moon, but an irregular titan forged in a forgotten era. Pitted ice, metallic veins, fractures sealed by eons of vacuum. Its surface reflects almost no sunlight, its face is as dark as the void behind it, yet beneath this exterior lie secrets that predate Earth's oceans and continents. There is no guidance system, no propulsion, only the memory of a birth in the thick disk of the Milky Way billions of years ago, where violent stars once blazed and died. In that epoch, radiation sculpted matter in strange ways. Collisions fused metals and gases into shapes no human hand has ever touched. 3i Atlas is the last surviving witness to that violence. As the comet drifts forward, the solar system begins to sense an intruder. The first to respond to its presence are not humans, but the outer reaches of the sun's gravitational field. For the countless millennia, this boundary has caught comets and asteroids from the Dirac cloud, shaping their paths into graceful loops. But Atlas does not obey those familiar patterns. It slices through space with an energy too great to be contained, its speed the signature of deep interstellar travel. Every kilometre it advances carries ancient stories, supernova dust, the scars of high-velocity collisions, fragments from worlds that may never have formed. The planets continue their silent orbits, unaware of the visitor streaking toward them. Jupiter spins with its belts of cloud. Saturn traces its path like a timepiece, Neptune drifts in blue solitude. And all the while, Atlas approaches uninvited and indifferent. It is not malevolent, nor is it purposeful. It is simply a force older than intention, carrying within its core a mass that could rewrite the history of any world unfortunate enough to cross its trajectory. Far from Earth, on the scale of millions of kilometres, the comet glows faintly as solar radiation begins to reach it. A thin mist of vapour escapes from microscopic cracks. Dust dormant for billions of years loosens and drifts into space. Atlas is waking not in consciousness, but in activity, shedding the first hints of the luminous veil it will soon wear. Its coma, once inert, now begins to grow stretching like a ghostly halo around the unlit rock. The tail forming behind it is not just beautiful, it is a warning. On Earth, telescopes continue surveying the sky for the usual signatures of comets and asteroids bound by the sun's influence. Observatories track fast-moving objects, but none have yet noticed the subtle arc that Atlas cuts across the firmament. It is still too far, still too faint, still too perfectly aligned with the glare of distant starlight. But its velocity will betray it soon. When its approach becomes unmistakable, it will ignite a storm of scientific fascination and existential fear. For now, it remains a ghost. Imagining the comet in this moment, quiet, ancient, unstoppable, invites a shiver that has nothing to do with cold. It is the realization that the universe does not revolve around human timelines or expectations. Objects like Atlas drift between stars without purpose, yet they hold the power to make entire histories. The cosmos does not negotiate, it only delivers consequences. The space between Atlas and Earth is still immense, measured in hundreds of millions of kilometres. Yet in cosmic terms, this distance shrinks quickly. Every second the comet advances at tens of kilometers faster than anything humans can launch, faster than any known natural object that orbits the sun. Its kinetic energy, quiet now, will one day equal the force of many extinction-level events combined. Still the comet drifts on, and still no one has given it a name. Its path is elegant in its inevitability, drawn by the sun's pull but shaped by a momentum forged in the galaxy's elder regions. It does not bend easily. It does not slow. In its ancient core, frozen gases wait to erupt into violent plumes as it nears the warming light of the inner solar system. Metals sleep beneath its crust, protected by vacuum and time. For billions of years, Atlas has been a story without witnesses. Now, as it enters the realm where human eyes may finally detect it, the mystery begins to sharpen. A single question takes shape, fragile yet immense. What happens when a relic of another star system older than Earth itself meets the home of a young, fragile civilization? The universe offers no reassurance, only silence and a cold path cut through space. The first glimpse came not with spectacle, but with a whisper, an anomaly buried within a crowded field of distant stars. It arrived as a smear of faint motion recorded by a telescope designed to catalogue objects far more predictable. The observatory responsible for this discovery was not expecting anything remarkable that night. The team was conducting routine sky surveys, tracking objects locked in the familiar loops of our solar system. But the software flagged something unusual, a point of light shifting position faster than expected, its vector cutting across the background with an indifference that betrayed no allegiance to the sun. At first, astronomers suspected an error. High-speed intruders are rare and the sky's filled with noise reflections, cosmic rays, optical artifacts that can mimic movement. But the data held steady. Across several exposures, the object carved a clean diagonal, its brightness consistent enough to dismiss equipment malfunction. When its trajectory was modelled, the conclusion fell like a stone. This body was not bound by the sun's gravity. Its speed exceeded the escape velocity of the solar system. It was coming from deep space. The object earned its provisional designation 3i Atlas. The 3i marking placed it among a tiny elite category, only the third interstellar visitor ever officially recorded. Before it came 1i Oumuamua, the cigar-shaped mystery that puzzled scientists in 2017, and 2i Borisov, whose brilliant coma revealed a more comet-like origin. But Atlas was different. Earlier interstellar objects had been fleeting small, difficult to measure. This one was brighter, larger, and travelling on a hyperbolic path of such clarity that there could be no doubt. It had come from elsewhere, another star, another time, another cosmic narrative entirely. As observatories around the world turned their attention toward it, the strangeness mounted. Its motion was too rapid for standard asteroid classification. Its brightness fluctuated in a way that suggested volatile outgassing, yet the pattern did not match typical solar system comets. Even more perplexing was its preliminary spectral analysis. Light reflected from its nucleus contained signatures of an older chemical mix, including elevated nickel and iron levels, a clue pointing not to our gentle galactic neighbourhood, but to a harsher, more violent birthplace. All this added to a growing sense that scientists were glimpsing something extraordinarily ancient. The comet's origin was soon traced backward through the galaxy. Simulations indicated it had emerged from the Milky Way's thick disk, a population of stars older than the Sun by billions of years. These stars formed during a turbulent epoch when radiation fields were intense and interstellar collisions frequent. In such a crucible, materials fused into exotic blends. Atlas, born amid that violence, had carried its elemental memory across eons. By the time it neared the solar system, it was likely older than the continents, older than Earth's oceans, older than the very planet that now watched it with uneasy fascination. Telescopes like Hubble and Pan-STARRS sharpened their focus. The object was measured to be hundreds of meters across at minimum, possibly exceeding 5 kilometers, monumental for an interstellar visitor. Its surface revealed a lumpy silhouette veiled by jets of water vapor and carbon dioxide erupting from fissures warmed by the sun. Unlike Oumuamua, which never displayed a comet's typical halo, Atlas responded vigorously to solar radiation. Its coma bloomed outward, a growing shroud of dust and ice that hinted at internal reservoirs untouched since the universe was young. Astronomers tried to predict its future path, and here another shock emerged. Although the official trajectory placed Atlas safely distant from Earth, its closest approach would be nearly 2 astronomical units. Minor uncertainties remained. The forces acting upon comets are not merely gravitational. Outgassing can alter trajectories subtly but significantly, and interstellar objects often behave in ways no model anticipates. Every plume, every spin, every emission of gas created microthrusts that had to be accounted for. For the scientific community, this unpredictability was thrilling. For atmospheric modelers and impact analysts, it was unsettling. The discovery ignited a wave of studies across universities and space agencies. The Interstellar Object Rapid Response Network assembled teams to analyze its potential risks. Not because it appeared dangerous, but because interstellar objects often defied expectations. Scientists recalled how Oumuamua had unexpectedly accelerated as it left the solar system, a mystery that sparked debates ranging from hydrogen outgassing to the outlandish idea of artificial propulsion. Atlas, larger and more volatile, might possess secrets more profound. The comet's rotation rate was next to draw attention. Observations suggested a chaotic spin wobbling rather than turning smoothly. This indicated an irregular mass distribution likely caused by impacts long ago. Such a spin pattern also implied internal stress, meaning Atlas could fracture or erupt unpredictably as it warmed. If a major outburst occurred at the wrong moment, its trajectory could alter by tens of thousands of kilometers. Astronomers refined their calculations daily, adjusting for each new plume of gas detected. Still, despite the uncertainty, the object was hailed as a scientific treasure. Researchers studied the tail's evolving length, analyzing particles that had drifted untouched across billions of years. Spectroscopy revealed the pristine chemistry of early galactic formation molecules that might illuminate how planets first condensed around distant suns. Every fragment in the coma carried a story older than the solar system itself. For planetary scientists, it was like reading a chapter of cosmic history thought forever lost. The world's largest telescopes followed it relentlessly. Observatories captured its growing brightness and mapped its coma's expansion. Amateur astronomers across the globe joined in, though the object's motion made it difficult to track with consumer equipment. Yet even blurry images were shared widely online, fueling public fascination. This was not just another comet from the Oort cloud. It was a messenger from beyond, an ambassador of unknown physics, an artifact of time's deeper layers. As excitement grew, one unspoken question lingered. What if its path changed? What if the universe in its endless indifference shifted the course of this ancient wanderer? The probability was infinitesimal, but not zero. Scientists avoided sensationalism, choosing instead to focus on what could be learned. But beneath their analyses, beneath the mathematics and spectroscopy there, remained the quiet awareness of vulnerability. Earth had been struck before, and in this vast, unpredictable galaxy it could be struck again. But Atlas still travelled far beyond the orbit of Mars, and its faint light carried only promise, not threat. For now, it was simply a discovery, a glimpse into the distant past, a rare visitor crossing the boundaries of worlds. Its presence was a reminder that the universe is larger than imagination, and older than memory, and full of wanderers that carry with them the echoes of forgotten stars. In those early days, before any talk of danger emerged, Atlas inspired awe more than fear. It seemed a cosmic gift, a relic arriving from the dark to offer humanity a chance to look backward into the galaxy's youth. No one yet imagined that tiny changes in its motion, sparked by forces too subtle to predict, would one day shift the narrative from curiosity to catastrophe. For now, astronomers simply watched, measured, and wondered what secrets this traveller would reveal as it drifted closer to the warmth of the sun. Long before the sun ignited its first fusion reactions, before Earth's oceans formed or its continents cooled, the Milky Way was a different place, wilder, brighter, more violent. In that ancient era when the galaxy's thick disk was still being sculpted by waves of star formation and collapse matter, existed in a state of cosmic turbulence. Giant stars lived fast and died explosively, scattering metals in great floods across interstellar space. Radiation from newborn suns carved cavities in gas clouds, and shockwaves from supernovae collided like overlapping storms. In this age, the ingredients for worlds were raw, volatile, and constantly shifting. It was here in this early furnace of creation that the object humanity would one day call 3i Atlas was born. The thick disk of the Milky Way is older than the thin disk where our solar system resides. Its stars are ancient, some 7, 8, even 9 billion years old. They formed when the galaxy itself was still assembling its identity. The region was denser, then packed with unstable protostars, colliding clouds and heavy elements forged in the hearts of the first supernovae. Any body forming in such an environment would inherit a chemistry unlike anything common today. Atlas emerged from this crucible as a mixture of metals, carbon dioxide, ice, primordial dust, and compounds forged in radiation fields no longer present in the modern Milky Way. Its initial shape was no doubt changed by countless impacts because in that epoch, collisions were not rare events but rites of passage. The object was likely once part of a larger body, perhaps a forming planet or planetesimal orbiting an early unstable star. But gravitational chaos tore such systems apart. A passing star or a supernova shock front could have unbound Atlas from its birthplace, flinging it into the galaxy with a velocity far exceeding the escape speed of its parent system. Once released, it began a journey that would outlast civilizations, continents, and geological ages, drifting through interstellar space. Atlas encountered environments few objects survive. Radiation from passing spalled atoms from its surface. Dust at hypersonic speeds chipped miniature craters into its crust. Cosmic rays passed through it like needles of invisible fire, splitting molecules, altering minerals, gradually transforming the object's interior into a tapestry of ancient chemistry. Yet the comet endured. Its metals resisted erosion. Its ices, shielded within layers of regolith, remained frozen across unimaginable stretches of time. If Atlas had consciousness, it would have witnessed the galaxy evolve around it, when the proto-sun ignited and planets began forming around it. Atlas was already ancient, carrying memories older than Earth's bedrock. When early life on our planet first stirred in warm, shallow seas, Atlas was drifting between stars whose names we will never know, and as the age of dinosaurs rose and fell, the comet continued its silent pilgrimage across the void, unaffected by the dramas of evolving ecosystems and extinction events. Astronomers studying Atlas's composition realized quickly that it bore the hallmarks of this ancient lineage. High nickel and iron concentrations in its gases were startlingly unusual for comets born within our gentler region of the galaxy. These metals suggested origins in a part of the Milky Way where star formation occurred under extreme conditions. The particles released from its surface, captured through spectroscopic analysis, hinted at temperatures and pressures not seen near our Sun. Everything about Atlas spoke of a past lived far from the solar system's comparatively quiet nursery. Its age, though impossible to measure precisely, could be constrained through models of galactic motion. The trajectory simulations indicated that Atlas had wandered freely for at least several billion years, possibly more than 7 billion. It was a relic from a time before Earth existed, before the Moon formed, before the Sun coalesced from its molecular cloud. It predated the solar system by a span longer than the entire evolutionary history of terrestrial life. As researchers pieced together this cosmic biography, a sense of reverence emerged. To observe Atlas was to observe the galaxy's memory. It carried within it fingerprints of astrophysical processes long vanished. Its frozen gases preserved the chemistry of an era inaccessible to even the most powerful telescopes. Its metals were forged in stars that had lived and died before Earth's atoms even formed. The comet's surface, dark as obsidian, was not merely ancient, it was primeval. Each fissure told a story of radiation storms. Each metallic seam whispered of the violence that gave birth to heavy elements. Even its chaotic spin, wobbling unpredictably as it tumbled through space, was a consequence of billions of years of micro-impacts and thermal stresses endured without witness. Astronomers studying Atlas found themselves holding a rare key to understanding the early galaxy. Interstellar objects are time capsules capable of revealing how matter behaved before the Milky Way settled into its current form. By examining Atlas, researchers could peer past the solar system's birth, past the age of planet formation, into a deeper, more ancient chapter of cosmic history. The comet became more than a scientific curiosity. It became a clue, a fragment of an ancestral archive scattered across the galaxy. In its chemical signatures were encoded the stories of ancient stars. In its motion was the echo of violent gravitational upheavals long extinguished. And in its icy core was the memory of conditions no longer reproducible anywhere near Earth. Yet as Atlas moved closer to the Sun, awakening from its frozen slumber, it revealed another truth. Ancient objects are unpredictable. Their internal structures are weakened by time, their materials respond explosively to heat after eons of cold. The very age that made Atlas scientifically precious also made it dangerous, for such relics do not behave like younger comets shaped by the orderly cycles of the solar system. Still within this danger lay a profound sense of wonder. Humanity was observing something older than itself. Older than its world, older in fact than nearly everything familiar in the night sky. Atlas carried the story of the galaxy's youth written in dust and frozen gas carried across billions of kilometers and billions of years, and now for reasons no more complex than gravity and chance that story was intersecting with Earth's. What began as a faint point of motion on a telescope's CCD was quickly becoming one of the most significant scientific discoveries of modern times, a relic of cosmic antiquity hurtling toward the inner solar system, bearing with it a past so vast and remote that human history seemed no more than a brief flicker by comparison. In the shadow of such enormity, one realization lingered: if an object this old could survive long enough to cross paths with Earth, then the universe was still full of wanderers, each carrying its own ancient secrets. And not all of them perhaps would pass by harmlessly. The first models came back with numbers so large they felt unreal, almost theatrical figures that belonged to simulations of dead worlds, not to the quiet fragility of Earth. The comet's velocity was the first variable that unsettled scientists. Interstellar visitors travel differently. They do not spiral inward slowly like long-period comets from the Oort cloud. They plunge, they descend upon the solar system with the momentum of ancient journeys lasting billions of years. And Atlas, born in the galaxy's thick disk and unbound by any gravitational leash for ages, uncounted, surged through space with a speed that dwarfed anything humanity had ever confronted. By the time it crossed the outer planetary orbits, Atlas was already travelling at more than 60 kilometers per second, 3 times faster than the asteroid that ended the age of dinosaurs. And that was only its minimum measured velocity. Gravity from the sun would accelerate it further, drawing it inward like a falling blade, gaining speed with every heartbeat. This single variable velocity placed Atlas into a category of threat rarely even contemplated in planetary defense scenarios. A smaller object at that speed would strike like a larger one. A medium object would strike like a titan, and a titan would strike like a moment of extinction written into the bedrock of a world. Astronomers ran the kinetic energy formula again and again as though repetition might soften the result. It did not. No matter how they adjusted the assumption density-diameter angle of approach, the output remained catastrophic. If Atlas ever deviated toward Earth even slightly, it would carry the energy of multiple Chicxulub-class impacts. Not once, not twice, but many times over. This was not merely surprising, it was scientifically staggering, because in physics size is not the sole measure of destruction. Energy is, and energy scales with the square of velocity. That meant Atlas's incredible speed did more than increase its danger, it redefined it. A body half the size of the Chicxulub asteroid moving 3 times faster would not produce half the devastation. It would produce several times more. In computer models, the impact signature of Atlas did not resemble traditional cometary strikes. It resembled a planetary-scale injection of energy, an event that could set forests ablaze continents away, boil oceans into towering storms, and generate shockwaves that encircled the globe. The scientists studying its motion understood the implications. They held meetings behind closed doors not because they had something to hide, but because raw data of this magnitude demanded careful interpretation. Specialists in celestial mechanics examined long-arc predictions. Planetary geologists simulated cratering effects in early test runs. Atmospheric physicists analysed the range of uncertainties in the event of an Earth-crossing trajectory. Clean empirical numbers told a story more chilling than any dramatic headline could invent. Atlas was a carrier of extinction-level energy. Even a glancing encounter, even a fragment of it, would be enough to tear open the planet's stability. It was the object's strangeness, however, that caused even deeper unease. Atlas behaved irregularly. His jets of gas erupted, unevenly altering its course by small but measurable degrees. Unlike Oort cloud comets, whose behaviour can often be predicted with careful modelling, interstellar objects arrive with unknown internal structures. Their ices respond differently to heat. Their surfaces fracture in unexpected ways. Some develop sudden torques that redirect their motion. Others rotate so chaotically that trajectory calculations become exercises in controlled uncertainty. Atlas exhibited all of these traits. Its coma was asymmetrical. Its tail flickered and shifted like a flame disturbed by unseen winds. Spectroscopic readings suggested that volatile ices lay beneath layers of metal-rich crust, an unusual configuration that could create violent outgassing events as it warmed. Each event, even if minor, could bend its path just enough to alter long-term projections. And when an object is moving at tens of kilometers per second, even a small deflection can translate into millions of kilometers over time. This unpredictability led scientists to contemplate what would have been unthinkable only years earlier: the possibility that Atlas, through a statistical fluke or a chain of microforces, might one day intersect Earth's orbit. To be clear, the probability remained low, but in cosmic mechanics, low is not zero. And when the stakes involve the survival of ecosystems, biospheres, civilizations, and the continuity of evolutionary history, even a distant chance becomes a subject of profound concern. The discovery of the comet's metallic signature intensified this anxiety. Its elevated nickel and iron content suggested tremendous internal strength. Unlike fragile Oort-cloud comets which can fragment before reaching the inner solar system, Atlas was robust. It would not crumble easily. It would not disintegrate safely into a harmless shower of dust. It was an object forged in the galaxy's violent youth, dense, ancient, and hardened by billions of years of exposure. It would reach Earth's atmosphere intact, and it would strike with a force our world has not seen in tens of millions of years. Yet the shock was not merely physical, it was conceptual. The solar system was once thought to be a sealed realm, a quiet sanctuary where threats came from known directions, bound by gravity and predictable across centuries. But interstellar objects like Atlas shattered that illusion. They arrived from the dark between stars. They carried velocities that defied local patterns. They had compositions alien to our planetary family. And most importantly, they reminded scientists that Earth exists not in isolation, but within a galaxy filled with ancient debris moving freely and unpredictably. The shock was a philosophical one as much as a scientific one. If objects like Atlas wander the galaxy in numbers greater than we once believed, then the history of Earth may owe its stability to little more than luck. Luck that no interstellar body had previously crossed our path at the wrong moment. The thinness of that fortune became painfully clear when researchers plotted Atlas's backward trajectory. For millions of years it had been passing within tens of millions of kilometers of other star systems. Its path had been shaped by gravitational brushes, with unseen worlds by flybys of stars that had long since drifted apart. All it would have taken was one small encounter, a passing star, a molecular cloud, a fragment of another comet to shift its arc through space in such a way that Earth billions of years later would be placed in its shadow. And now here it was entering the inner solar system with a speed born of the galaxy's early fires, carrying enough energy to end the evolutionary story of Earth in a single instant should chance align the paths. No one spoke openly of doom. No one claimed certainty where none existed. But a quiet understanding settled over the scientific world. Atlas was not merely an object of study. It was a reminder etched in ancient metal and ice of how fragile the past has been and how undecided the future remains. And as the comet continued its relentless descent toward the inner planets, the mystery that surrounded it grew darker, heavier, more urgent. The shift began with a tremor so small it almost blended into the background noise of astrophysical uncertainty, a faint deviation in the comet's predicted position, barely more than a rounding error. At first, no one treated it as significant. Comets breathe as they warm. Their jets pulse their surfaces, fracture their orbits, adjust in tiny increments. Atlas, volatile and ancient, was expected to drift slightly off course as it approached the Sun. But this deviation did not fade with further measurements. It grew, it compounded, and suddenly a trajectory once plotted with comfortable margins began to bend toward a more troubling arc. The models updated daily began showing a pattern that made astronomers tighten in their seats. The new calculations suggested a small change in the comet's motion, just a few fractions of a degree. Yet over tens of millions of kilometers, such a change amplified to alarming proportions. It was still nowhere near a guaranteed impact. But the possibility now existed in a space where calculations had once returned zeros. The turning point came from a subtle burst of outgassing detected near the comet's subsolar point, the region directly facing the Sun, where internal heat first penetrated into its frozen layers. That eruption was not symmetrical. It vented from a fissure discovered days earlier, in high-resolution imagery sending jets of gas and dust shooting into space like the exhaust plume of a rotating engine. The thrust was tiny, imperceptible to the naked eye, but it was persistent. And in orbital mechanics, persistence matters. It nudges, it tilts, it pushes. Within a week of new observations, the effect became undeniable. Atlas was shifting. The room where the trajectory team convened normally, a place of casual collaboration, grew colder, quieter. They worked through the night, rechecking assumptions, recalibrating and input values, feeding updated spectroscopic data into their propagation algorithms. But no matter how meticulously they refined the equations, the result converged toward the same troubling insight: the comet's path was drifting closer to the plane of Earth's orbit. This was not yet a collision course, but it was no longer impossible. The realization spread through scientific circles with a kind of restrained urgency. Emails exchanged among planetary defense researchers lost their usual academic calm. Analysts who had once spoken about Atlas with awe now spoke of it with a tone that hinted at something heavier, something like foreboding. There were no press releases, No alarm bells, just careful conversations about uncertainties impact windows and the fine line between a harmless flyby and a planetary tragedy. The moment of collective stillness arrived, when updated models produced their first keyhole analysis, a calculation identifying narrow gravitational passageways that could set the comet on a long-term trajectory toward Earth after its solar approach. These keyholes were small, some no wider than a continent. But if Atlas passed through one of them at precisely the right angle, the Sun's gravity would alter its outbound path, sending it on a future orbit intersecting Earth with devastating precision. Such scenarios were remote, but their existence was enough to shift the tone. Scientists who had once marveled at the object's ancient origin now found themselves contemplating the ways in which a small shift in gravitational geometry might determine the fate of an entire biosphere. The solar system, once mapped and predictable, now felt like a place of fragile alignments and precarious balances. The escalation continued as the comet drew closer. Its jets grew stronger, its rotation more erratic. Each plume of vapor released into space subtly adjusted the comet's center of mass, sending it into tumbling motions that made predictions increasingly difficult. Instruments aboard deep space telescopes detected sudden flares of brightness, evidence of fresh vents, opening perhaps due to internal pressure building from the sun's heat. Every new plume introduced a new variable. Every variable widened the uncertainty. The phrase trajectory chaos began appearing in internal reports, and with the chaos came dread. The question shifted from what is Atlas to where will Atlas be? The two were no longer academic curiosities, they were potential determinants of planetary survival. For the first time, the possibility of an Earth-crossing orbit was discussed not as science fiction, but as a branch of the probability tree, slender yet real. To make matters worse, gravitational perturbations from Jupiter, subtle but measurable, introduced additional complications. A pass near the gas giant could magnify the comet's unstable motion. Jupiter, with its immense gravitational field, has a long history of redirecting comets in unpredictable ways. Sometimes it shields Earth by ejecting objects from the solar system entirely. Sometimes it sends them inward on new treacherous paths. Atlas, arriving with an interstellar velocity and a volatile composition, was uniquely sensitive to these interactions. Trajectory simulations split into families, thousands of potential futures branching outward like fractal limbs. Most were benign, a few were catastrophic, and the closer Atlas came, the more those families shifted, twisted, and evolved. What had once been an abstract risk was now a dynamic, real-time question that could not be dismissed. The sense of escalation was not just numerical, it was emotional. Observatories reported increasing difficulty predicting the comet's behavior. His jets became irregular, bursting like erratic geysers with every new rotation. Its coma thickened, shrouding parts of the nucleus and making center-of-mass calculations more error-prone. Each update carried a slight recalibration in its path, a small tilt that extended or reduced Earth's safety margin by millions of kilometers. The scientific world felt the pressure of cosmic contingency and understanding that the fate of a civilization could hinge on the thermal fracture of a single fissure on an object older than Earth itself. Perhaps the most unsettling shift came when new data from a series of long-range radar pings revealed an asymmetry in the comet's density distribution. Parts of Atlas were denser than expected, likely containing metallic inclusions large enough to alter its response to solar heating. This irregularity meant that Atlas could rotate erratically, under thermal stress, amplifying the unpredictability of its spin state and by extension its trajectory. One astrophysicist described the scenario in an internal memo as a celestial coin toss, where the coin weighs billions of tons. It was no longer enough to trace the comet's path. Scientists now needed to anticipate the unanticipatable, the exact moments when outgassing events might erupt, the structural weaknesses that might open under heat, the mass redistributions that could flip its spin. In planetary defense simulations, the line between safe passage and collision narrowed. And though no one would say it publicly, everyone understood the implication an ancient wanderer had begun its slow alignment toward Earth's orbital lane. Not out of malice, not out of intention, but out of the simple, indifferent interplay of gravity, time, and chance. Forces older than life, older than planets, older than the very stars that now watched the unfolding of this ancient object's return to light. Atlas had shifted. The universe had decided nothing. But Earth's margin of safety had grown thinner, and the descent continued. As the comet drew closer to the inner solar system, its true nature unfolded in layers, each revelation deepening the sense of unease that already surrounded this dark wanderer. Telescopes that once captured only faint silhouettes now resolved the object in sharper clarity, illuminating a nucleus unlike any comet previously documented. Atlas did not present itself as a simple ball of ice and dust. It was a fractured world, let an ancient shard of cosmic violence suspended in a body whose complexities defied easy categorization. At the core of its strangeness was its shape an irregular contorted mass, with ridges and depressions that suggested catastrophic upheavals in its distant past. High-resolution images revealed elongations and protrusions fragments that resembled fused boulders welded together by time and pressure. The surface bore scars, deep fissures zigzagged across plains of darkened ice, some large enough to expose metallic underlayers buried beneath the dusty crust. These metals, rich in nickel and iron, glinted faintly under the sun's growing influence, mirroring nothing seen on typical solar system comets. This ancient metallurgy puzzled scientists. In normal cometary bodies, metals exist only in trace quantities mixed loosely with silicates and frozen volatiles, but Atlas held dense metallic clusters embedded throughout its structure, evidence that it formed in a region shaped by supernova debris, an environment where elements heavier than iron were blasted into surrounding material. The comet's composition suggested a birthplace where stellar explosions repeatedly swept through forming systems fusing matter in ways that no longer occur near the sun. As the object warmed, instruments detected plumes erupting from its surface, jets of carbon dioxide, water vapor, and metallic dust, each plume emerging with startling violence from isolated vents. These eruptions painted an evolving picture of Atlas's internal complexity. One plume burst from a crater-like depression, whose rim exhibited strange coloration, possibly from oxidized nickel or silicate mixtures altered by cosmic rays. Another erupted from a fractured ridge, sending a spiraling jet into space that extended thousands of kilometers behind the comet. Unlike typical comets whose outgassing patterns often reveal symmetrical heating responses, Atlas vented in asymmetrical fits. Some days produced barely any activity. Others erupted in flares that increased the comet's brightness by entire magnitudes. This inconsistency served as a stark reminder that the object was far older and more structurally complex than anything humanity had previously monitored. Its jets rotated unpredictably as the body tumbled through space, and with each new eruption, its spin changed. The rotation period fluctuated, oscillating between long, slow turns and spasms of rapid reorientation. The comet spun like a wounded celestial beast, one that had carried its injuries for billions of years. The motion of dust around Atlas offered further clues to its strangeness. High-speed cameras captured grains spiraling around the nucleus in chaotic patterns, their trajectories bent by irregular magnetic fields likely generated by metallic inclusions within the body. No ordinary comet possessed such subtle magnetic distortions. These patterns suggested that Atlas's interior might not be entirely inert. Perhaps pockets of trapped gases expanded beneath layers of dense metal, causing pressure waves to ripple through the crust. Or perhaps the nickel-rich regions interacted with solar radiation differently, generating localized magnetic behaviors unseen in younger cometary bodies. Its tail, too, defied expectations. Depending on the angle of solar exposure, the tail split into multiple strands, some narrow and filamentary, others broad and diffuse. These strands carried distinct chemical signatures indicating a layered internal composition. One strand contained grains of carbon dioxide frost. Another revealed heavy ions and microscopic metallic dust. This segmentation hinted at the comet's long, violent past, a history of being broken apart and reassembled under gravitational stresses that spanned eons. The tail's structure also revealed a troubling truth. Atlas was shedding material at an accelerating rate. Each new venting event expelled thousands of tons of debris, both icy and metallic. And as this material shot into space, it influenced the comet's motion, pushing and pulling it in unpredictable directions. The object's instability was no longer just a scientific observation, it had become a central factor in understanding the threat it posed. Radar imaging exposed even deeper layers of complexity. Penetrating the outer crust, radar waves returned data indicating cavities within the nucleus hollow chambers left by long-evaporated volatile reservoirs. These internal voids made Atlas structurally fragile yet deceptively resilient. In some comets, such cavities lead to fragmentation, but Atlas's metallic composition gave it strength. It could survive enormous internal pressures without breaking apart. This was both fascinating and terrifying. A comet that refused to fragment was a comet that would reach Earth intact if its path ever shifted toward collision. Its chaotic spin added another layer of danger. The comet rotated about multiple axes, wobbling unpredictably as sunlight heated different regions unevenly. Rotational instability can lead to sudden structural collapse in younger comets, But Atlas, hardened by billions of years of cosmic exposure, absorbed these stresses without shattering. Instead, its rotation changed in ways that defied simple modelling. One moment it spun slowly, exposing a broad metallic flank to sunlight. The next, it snapped into a faster rotation, exposing new vents that triggered additional jets. With each rotation cycle, its coma reshaped itself, trailing behind in ever-shifting curtains of gas and dust. When scientists attempted to model these behaviors, their simulations repeatedly failed to converge. Atlas did not act like an object born in the solar system. It did not follow predictable patterns of heat response or structural stress. It behaved like something shaped in an environment of extremes, massive radiation, rapid thermal cycling, violent collisions. Each new measurement hinted at more layers of complexity. Each new discovery hinted at greater instability. And instability for an object moving at such speed was not merely an academic curiosity. It was a harbinger of danger. Every venting event, every plume, every rotational shift introduced new variables into the comet's trajectory. These subtle nudges compounded like whispers, turning into echoes, pushing Atlas into an ever more uncertain path. Observatories tracked its position with increasing urgency, feeding fresh coordinates into predictive models that grew more chaotic with each passing week. The comet's strange makeup, its metals, its ancient ices, its fractured yet stubbornly intact form, was not just a scientific marvel, it was a threat multiplier. Because in planetary defense, predictability equals safety. Unpredictability equals danger. Atlas was becoming more unpredictable by the day, and as the comet crossed into the region where solar heating intensified, its most volatile components had not yet awakened. Scientists knew the worst outgassing, the most violent structural changes were still ahead. The shape of doom had revealed itself, but its story was far from finished. The numbers as appeared on the screen like a quiet betrayal, columns of data, rows of probabilities, and at the far end of the table, the one result no one wished to see: a non-zero impact likelihood. It was small, yes, vanishingly small, but not zero. And when the object in question carried enough kinetic energy to redraw continents, even a slight shift in probabilities felt like the closing of a door. The calculation that sent a chill through the scientific community emerged not from a single observation, but from a convergence, new imagery revealing fresh outgassing, plumes, updated rotation state measurements, and a refined understanding of Atlas's asymmetrical structure. These inputs combined into orbital models produced an outcome that halted conversations mid-sentence. A narrow corridor of gravitational geometry, one of those cosmic keyholes that space agencies study with near-religious seriousness, now intersected with Atlas's possible path. If the comet passed through this corridor even by tens of kilometers, its outbound trajectory would bend into a fatal loop. It would return. Not on its current hyperbolic path, which would carry it safely out of the solar system forever, but on a new trajectory gravitationally reshaped by the sun, aimed squarely at Earth on its next pass. The shock was not the present-day threat. It was the understanding that future catastrophe could be seeded not by a dramatic collision today, but by an invisible nudge unfolding in silence witnessed only by equations. The room where the analysis was conducted fell impossibly still. Astrophysicists who had spent careers studying celestial mechanics, a discipline defined by elegance, now stared at data that felt heavy, even ominous. Space so vast and so indifferent had revealed a tiny passageway through which fate could thread a needle, and the needle was moving toward it. The simulations continued running through the night. Thousands of variations, thousands of subtle changes in orientation, velocity, thermal response. Each iteration generated cascading differences. Some trajectories placed Atlas comfortably far from the keyhole. Others passed dangerously close, a few disturbingly slipped directly through. No one panicked. Scientists rarely do, but the sense of unease that settled over the team that night was unmistakable. A comet older than the solar system, forged in the galaxy's violent youth, was now hurtling through a mechanism of gravitational precision too delicate to fully predict. And somewhere in that immense unfolding clockwork, humanity's margin for error narrowed. What deepened the dread was the energy calculation that accompanied the updated trajectory models. Atlas's speed approaching extraordinary values as it neared the sun transformed its potential impact energy into something beyond familiar disaster scenarios. The Chicxulub impact, long held as a benchmark for planetary devastation, became a reference point dwarfed by Atlas's kinetic profile. When the numbers were run through atmospheric and geophysical simulators, the software produced a model that caused one researcher to whisper, "This can't be right." But it was. A 5-kilometer interstellar comet traveling at 60-plus kilometers per second would deliver an impact energy equivalent to over 4.5 times the Chicxulub event. But this did not tell the full story, because its speed meant more than simple multiplication of destructive force. Atlas would deliver its energy not over seconds but over milliseconds, an almost instantaneous transfer of momentum that would vaporize rock-ocean atmosphere and crust. The shockwave would be so intense that bedrock at the point of impact would behave like liquid. Mountains would flatten, oceans would boil, the sky would ignite. This was not impact, it was erasure. The crater simulations reflected that. While Chicxulub carved out a basin over 100 kilometers wide, Atlas would produce a scar potentially approaching or exceeding that scale, depending on the density of the surface it struck. The crater depth alone could reach tens of kilometers, exposing the mantle in a wound that would take millions of years to fade from geological memory. The atmospheric consequences were worse. The models showed heat plumes rising thousands of kilometers, penetrating the upper atmosphere, tearing apart the ozone layer. The thermal radiation alone would ignite forests half a world away within minutes. Tsunami models produced waves cresting at unimaginable heights and traversing oceans, erasing coastlines. But the most chilling output was not the blast wave or the crater. It was the timeline. Time to mass extinction hours. Time to global ecological collapse days. Time to onset of multi-year impact, winter less than 2 weeks. And finally, expected survival rate of terrestrial megafauna near zero. Expected survival rate of humanity borderline theoretical. The room grew colder, not physically but perceptibly, as though the weight of the data dimmed the air itself. Scientists exchanged glances filled with a mix of disbelief and grim acceptance. The universe in its incomprehensibly vast theatre had delivered a simple truth through the cold precision of physics. If Atlas struck Earth, there would be no recovery. Civilization would not rebuild. Humanity would not adapt. This was not a catastrophe from which life could spring anew. It was a full stop in the evolutionary record. Yet the models were not predictions, they were possibilities. Warnings of what could be, not what would be. The comet still drifted millions of kilometers away. Its behavior remained chaotic, its future uncertain. But the door to a darker outcome had opened. The shock spread beyond planetary scientists to astronomers, geologists, atmospheric physicists, and even cosmologists. Research groups began exchanging urgent data packets. Agencies reactivated analysis pipelines that built for rare but critical scenarios: orbital uncertainty, resolution fragmentation modeling, worst-case contingency simulations. The language of quiet urgency appeared in internal memos. Trajectory refinement required. Non-gravitational forces must be reassessed. Further outgassing events expected. And then the line that froze every reader: impact scenarios cannot be fully excluded. To understand the dread that settled over the scientific world, one must remember, humanity has lived in a state of cosmic safety for millions of years. The solar system's architecture, stable and predictable, has permitted the rise of civilizations, ecosystems, and consciousness itself. But Atlas reminded scientists that this stability is not guaranteed. The galaxy is not gentle. It is a place of randomness, inertia, and ancient remnants drifting through the dark. And one such remnant, larger than most, older than nearly all, carrying within it the kinetic memory of billions of years of travel, now cast a shadow of possibility over a fragile blue world. It was no longer enough to admire Atlas as a relic of cosmic antiquity. It had become a question written in ice and metal, carried across epochs, now approaching the realm where answers matter. Would it miss? Or would it return? As Atlas crossed the invisible boundary separating the outer solar system from the inner sunlight, once a distant feeble glow began to strike its ancient surface with increasing intensity. For billions of years the comet had slept in the cold dark between stars, its ices inert, its metals silent. But now, as it drifted deeper into the realm of heat and radiance, the body awoke in stages, each reaction more violent than the last. Its transformation was not gentle. It was an eruption of memory, an ancient traveller rediscovering the warmth it had not felt since the galaxy was young. At first the changes were subtle. A thin wisp of vapour escaped from a crack along the comet's darkened crust. Then another, then dozens more. Under magnification these early jets shimmered, like pale threads drifting from unseen seams. But within days the trickles turned into eruptions. Internal pressures, long trapped beneath metal-rich layers, surged upward. CO2 ice sublimated in bursts, sending sheets of gas cascading outward into space. Dust grains, dormant for epochs, lifted into the void in glittering arcs. And the coma, once no more than a faint haze, began to swell. It expanded rapidly, first doubling in diameter, then tripling, then stretching into an enormous sphere of diffused brilliance. What had been a dim and distant nucleus now shone like a miniature star, wrapped in a shroud of glassy grey light. Observatories reported brightness increases so sudden they required recalibration. Atlas no longer resembled the dark interstellar stone catalogued months earlier. It had become a luminous apparition cutting across the firmament. The tail too transformed. Under the sun's growing influence, it stretched into an immense plume of ionized gas and dust arcing behind the comet in a sweeping arc thousands of kilometers long. Solar wind sculpted it, bending it into a luminous trail that rippled like a banner across the night sky. At its core, the comet's heavy metallic inclusions threw off faint electromagnetic signatures, adding a strange shimmer to the tail's edges, a phenomenon rarely observed in younger comets. Some nights the tail split into two luminous streams. One was the ionic tail, straight, narrow, pulled by the invisible hand of the solar wind. The other, broader and more complex, carried dust grains that glowed softly as sunlight reflected from their fractured surfaces. Instruments analyzing the dust revealed an astonishing mixture. Primordial carbon, nickel-rich fragments, silicates altered by cosmic rays. This was not just a comet tail, it was a drifting archive of the galaxy's ancient past. But if the object had become beautiful, it had also become dangerous. The comet's activity grew so extreme that its rotation state destabilized further. Each new outgassing event altered its angular momentum. The nucleus tumbled wildly, spinning on shifting axes, its orientation changing unpredictably with each jet. This chaotic motion made the object exceptionally difficult to model. Some nights its surface temperature fluctuated so rapidly that thermal fractures split new fissures along its crust. These fissures released yet more volatile material, triggering cascades of further unpredictability. And unpredictability for an object carrying extinction-level energy was not merely inconvenient, it was perilous. Ground-based observatories tracked the comet with increasing precision, but each day brought slight deflections, small yet impossible to ignore. A subtle change in brightness would hint at a fresh eruption. A dip in rotation speed suggested internal structural shifts. An asymmetric plume caused a measurable alteration in trajectory. These forces accumulated in ways no model could fully predict, creating a growing fear that the comet's path might wander into the narrow corridor that would alter its outbound orbit into a future collision with Earth. The closer Atlas came, the more intense the outbursts. Within the Comet's expanding sphere, scientists observed plumes reaching thousands of kilometers in length, towering geysers of dust and gas blasting into space before curling back under the influence of the comet's chaotic spin. In some regions, the jets were so forceful, they sculpted temporary cavities in the coma opening windows through which the nucleus could be glimpsed like a dark heart beating beneath a veil of living mist. Space agencies redirected satellites to observe the event. Solar observatories normally pointed toward the sun calibrated new settings to capture Atlas's luminous evolution. Even early warning asteroid systems designed to scan for local threats shifted focus. The comet dominated their horizon, a cosmic intruder whose behavior was rewriting the metrics of predictability. In the public sphere, the object became a spectacle. Images circulated showing a glowing blue-white streak cutting across the starfields, followed by a halo that shimmered like a ghost. Amateur astronomers, astonished by its brightness, photographed it with simple backyard equipment. Scientists cautioned against speculation, but fascination spread. People watched night skies for a glimpse of this ancient wanderer with a mixture of awe and trembling curiosity. Yet behind the scenes, the scientific tone had changed. The comet's outgassing had exceeded early predictions. Its chaotic rotation had accelerated. The coma's expansion hinted at internal pressure far greater than expected. And most alarming of all, the comet exhibited a pattern of recurring eruptions, episodic flares, that added small but irreversible nudges to its path. Even slight deviations at interplanetary velocities translated into millions of kilometers over time. The descent continued. As Atlas approached the orbit of Mars, passing nearer than any interstellar object had approached, a major planet in recorded history, solar heating intensified dramatically. The coma became a colossal sphere stretching hundreds of thousands of kilometers. Its tail, swept back by the solar wind, lengthened into a luminous ribbon, trailing deep into space. The comet had entered the region where solar radiation no longer warmed gently, it tore into the nucleus with unrelenting force. This phase marked the beginning of the final transformation. The object's ancient composition metals fused with primordial ices responded in ways that left scientists speechless. Some ices sublimated rapidly, generating walls of vapor. Others trapped beneath metallic layers built pressure until explosive vents erupted in spectacular arcs. These eruptions altered the comet's thrust with each rotation, creating an unpredictable dance between reaction forces and gravitational pull. Atlas had become not merely an interstellar visitor but a volatile engine of chaos, a luminous, unstable force spiraling toward the realm of Earth's orbit, and it was accelerating. The countdown had begun, not to impact yet, but to the moment when predictions would sharpen into either stability or doom. As the comet crossed the threshold into the inner solar system, its behavior intensified to levels that could no longer be treated as mere cometary physics. This was a cosmic event, unprecedented, ancient, and ominously alive. When Atlas finally breached the boundary of Earth's orbital lane, the world entered a state of suspended breath. The comet, once a distant curiosity, had become a roaring celestial phenomenon, shedding mass light and ancient memory in its violent descent. Yet nothing about its increasingly luminous presence hinted at the devastation that would ignite within seconds of atmospheric entry. If Atlas's future aligned toward collision, there would be no long approach, no warning streak across the sky, no moment for humanity to reflect. The timeline between entry and annihilation would be measured not in minutes, but in heartbeats. In every simulation, the first moment of contact unfolded the same way. As the comet slammed into Earth's upper atmosphere at more than 60 kilometers per second, the surrounding air compressed into a superheated plasma sheath. Temperatures soared higher than the surface of the sun. Molecules shattered. Electrons were stripped from atoms. Air became fire. The boundary between sky and stone dissolved in a shock front so bright it would overwhelm sensors before they could measure it. In the final second before impact, the comet would remain intact, a hardened relic of ancient astrophysics refusing to fracture. At that velocity, fragility offered no mercy. Even the vaporization of outer layers would not slow it. Atlas would plunge downward like a spear cast by the universe itself, carrying more energy than any explosive device humanity could imagine. Then the ground would rise to meet it. The instant the comet struck Earth, kinetic energy compressed into a single point. Stone, soil, and ocean, whatever surface lay beneath the comet's trajectory, would cease to exist, vaporized into incandescent plasma. The planet would respond as though struck by a star. A cavern of incandescent gases would open, expanding at hypersonic speeds, its shockwave traveling outward faster than sound could propagate through the crushed air. A fireball hundreds of kilometers across would bloom, turning night into white-out brilliance. The collapse of the crater's central region would occur almost simultaneously. Earth's crust, softened into a fluid state by unimaginable heat, would rebound upward, before splashing outward again in waves of molten rock. Material from deep within the planet, silicates, metals, vaporized minerals, would erupt into the air in plumes towering beyond the altitude where the atmosphere thins into space. The shockwave would flatten everything within a radius of 1,000 kilometers, not gradually but instantly. Forests would vanish, cities would become dust, oceans would rise in towering walls of displaced water. But the first second, those first 1,000 milliseconds, would not belong to fire or wind. They would belong to pressure. Pressure so intense that land and sea would flex downward like sheets of fabric. Pressure that would rupture tectonic plates. Pressure that would send seismic waves tearing through the mantle, igniting quakes at magnitudes beyond any recorded in human history. These waves would ripple around the globe, converging on the far side of the Earth, where they would erupt upward in a hemispheric echo of violence. Chicxulub left a crater 150 kilometers wide. Atlas, smaller but moving far faster, would carve a base nearly as large, its diameter determined not merely by size, but by speed. Some simulations placed the crater at more than 100 kilometers across. Others exceeded that projection, but all agreed the destruction would be absolute. The heat pulse following impact would spread outward at the speed of devastation. Forests would ignite hundreds of kilometers away. Water bodies would flash boil into steam. Animals caught beyond the blast radius far from the point of impact would experience blistering heat waves that left no time for escape. Anything exposed to sky would succumb within moments. The shockwave would circle the entire planet, a compression front of air moving so fast it would strip Earth from bedrock. Winds would exceed 1,000 kilometers per hour, beyond hurricane, beyond cyclone, beyond anything Earth's climate has ever produced. Even structures built to withstand war or disaster would crumble into debris. On the oceanic side of the planet, tsunamis triggered by the impact's momentum would tower higher than skyscrapers. They would travel across entire basins, erasing coastlines, sweeping continents, altering geography in hours. Land that had existed for millions of years would be cut, reshaped, or drowned beneath the weight of displaced oceans. But the most terrifying effect of the impact would occur above the planet, not upon it. Material ejected into the sky rock vapor, molten droplets, silicate dust, metallic fragments would rise into the atmosphere in a column of incandescent fury. As the plumes spread, it would blot out the sun across entire hemispheres. The thermal energy released into the upper atmosphere would burn through ozone, strip away protective layers, and ignite chemical reactions that darkened the sky with compounds no sunlight could penetrate. Much of the ejecta would leave the atmosphere entirely, scattering into space as glittering debris, forming a temporary artificial ring around Earth. But a greater portion would fall back days or weeks later as a barrage of superheated stones and glass-like fragments. These would ignite secondary fires across continents, creating a global inferno that rivaled the immediate blast in destructive power. Within an hour, the entire hemisphere facing the impact site would be engulfed in firestorm conditions. Within a day, global weather systems would collapse. Within a week, sunlight would dim to a fraction of its former strength, unable to penetrate the dense ash cloud spread around the globe. The world would enter the long night. But all of this, the fire, the shockwave, the oceans rising, the atmosphere boiling, was merely the beginning. The true horror lay in the aftermath, in the cold, in the silence, in the starvation that followed the fires, but those belong to later stages of the story. For now, in the scenario where Atlas strikes Earth, everything reduces to a single moment, the collision between an ancient interstellar wanderer and a fragile world not built to withstand such power. It is a moment of erasure, swift, brutal, absolute. And in that moment, Earth becomes a witness to the oldest truth of the universe. Energy does not negotiate. In the hours after the fires dimmed, and the shockwaves ceased their shuddering sweep across continents, the world entered a darkness deeper and more absolute than any night in human memory. It did not fall like a normal sunset with the slow softening of light and the patient rise of shadow. It arrived as a suffocation total, immediate and irreversible. The sky, swollen with ash and pulverized stone, sealed itself shut as though the heavens had turned to iron. Daylight struggled against the dense veil, but could not penetrate more than a faint, sickly glow. In place of sunrise came a dim, amber haze, the colour of cooling embers and the taste of dust. This was the beginning of the long night. In the earliest simulations, scientists had predicted that sunlight would dim by 90% following a Chicxulub-scale impact. For Atlas, the models were worse. Chicxulub had lofted hundreds of billions of tons of debris into the sky. Atlas, with more than 4 times its kinetic energy, generated trillions. The amount of fine dust hurled into the stratosphere exceeded any volcanic eruption in Earth's history. Every atmospheric layer became clogged with suspended particulates, silicate vapor that cooled into microscopic glass shards, carbon-rich dust, pulverized rock, and vaporized ocean salts. Each particle became a mirror reflecting sunlight back into space. Within days, the planet cooled dramatically. Surface temperatures plunged, humidity fell, winds weakened into heavy freezing currents. Oceans began to chill from above, forming layers of cold water that sank like lead and disturbed entire marine circulations. Across land and sea, the world slid toward a climate no living species had ever faced. Photosynthesis faltered first, leaves that had survived the fires wilted, trees shed foliage prematurely, grasslands faded into colourless mats, algae blooms collapsed in oceans and lakes. Without sunlight, the foundation of nearly every food chain snapped. Herbivores deprived of sustenance grew weak. Carnivores suffered soon after. Insects, those few not killed in the initial blast, faced a sudden scarcity of plant material. Even microbes in surface waters slowed, starved of the light that powered their ancient metabolic cycles. The silence deepened. Across entire continents, forests smouldered beneath layers of settling ash. Rivers turned opaque with sediment. Animals wandered through landscapes unrecognizable from days prior, charred, barren, dark. The sky's oppressive ceiling pressed downward, heavy with suspended soot thick enough to smother sound. Mountains vanished behind curtains of dust. Valleys filled with drifting particulates until the air itself felt solid. The Earth moved beneath the weight of a celestial bruise spreading across its atmosphere. Humanity, wherever it survived, the immediate catastrophe, faced its greatest challenge in this darkness. Solar power collapsed within days. Agriculture failed within weeks. Temperatures falling relentlessly transformed temperate regions into freezing wastelands. Even tropical zones cooled enough to kill crops. Within the first month, the planet's average temperature had dropped by more than 15 degrees Celsius. Within the second, by 20. Oceans froze at their edges, lakes solidified into opaque slabs. Ashfall became a continuous phenomenon. Tiny fragments rained down like powdered obsidian, coating the land in shifting layers. Every gust of wind stirred the accumulated debris into suffocating clouds. Breathing became difficult without filtration. Machinery clogged, transformers shorted, engines inhaled dust and died. Even nuclear facilities faced unprecedented complications as cooling systems struggled in the altered climate. Lightning storms flickered across the globe, fueled by the charged particles suspended in the atmosphere. These storms had no rain, only electric violence crackling through skies thick with ash. Occasionally superbolts struck the ground with devastating intensity, igniting new fires in a world already ruined by flame. But these fires were weak. They sputtered quickly, starved of oxygen in the increasingly suffocating air. Still the darkness persisted. Weeks passed. The sky remained sealed. Not a single clear day, not a single subtle stir. The world turned into a closed chamber lit only by the faintest reflections of sunlight bent and diffused by the particulate haze. Even at noon the land appeared as though lit by twilight. At midnight the darkness felt bottomless, an abyss from which no echo returned. In this prolonged shadow, ecosystems collapsed in sequence. First plants, then herbivores, then predators. Oceans followed in parallel. Without sunlight, phytoplankton died off en masse, robbing the seas of their primary oxygen producers. A cascade of biological failure swept across waters from coastal shallows to open ocean gyres. Fish populations crashed, marine mammals starved, coral reefs already fragile were entombed in darkness and sediments. The global air itself changed. With the loss of vegetation and the fires consuming what remained, oxygen levels began to drift downward, while carbon dioxide, temporarily suppressed by the dust veil, awaited its opportunity to rise again. The atmosphere oscillated between chemical extremes, struggling toward a new equilibrium. And at the core of these shifts was the absence of sunlight, the one stabilizing force Earth had always depended upon. What made this extinction winter different from all past cataclysms was the sheer volume of atmospheric debris. Atlas, older and denser than any comet born in the solar system, contributed not only dust but complex metallic aerosols. Nickel-bearing particles drifted through the sky. Iron-laced soot altered cloud microphysics. Strange chemical reactions occurred in the upper atmosphere as vaporized cometary compounds interacted with human-era pollutants. This fusion of ancient chemistry and modern industrial residue created compounds no model had fully anticipated. They absorbed light, they reflected light, they trapped heat incorrectly, they distorted infrared emissions. The result was a climate system unable to recover in predictable ways. Darkness persisted for months. Temperatures continued to fall, snowstorms blanketed equatorial regions, glaciers expanded outward. Oceans began forming thick crusts far beyond their usual polar boundaries. The long night tightened its hold, transforming Earth into a world that felt distant from its own past, a place of unending dusk where warmth became memory and light became myth. Humanity, huddled in pockets of artificial illumination, could only watch as the familiar rhythms of the planet unraveled. The long winter was not merely a season, it was a new age, one born in a single second of impact but destined to last for years. And in that darkness, the future narrowed, becoming not a horizon but a question. How long would the night endure? As the long night deepened, the world entered its second phase of collapse, a slower, more agonizing unraveling than the violent shock of the impact itself. In the first days, destruction had been immediate fire, shockwaves, tsunamis, and atmospheric ignition. But in the weeks and months that followed, the planet suffered a quieter catastrophe, one that seeped into every ecosystem, every biological chain, every reservoir of life. Earth did not simply go dark, it became chemically altered, poisoned from above and below, reshaped by forces set into motion the instant Atlas vaporized upon impact. The first sign of this deeper decline emerged as the dust clouds began to descend. What had once been a suspended veil now fell steadily, fine layers accumulating on every surface from the tallest mountain peaks to the deepest river valleys. This material, drawn from pulverized crust, vaporized ocean salts, and metallic fragments of the comet itself, coated the land in a grey mantle. But it was not benign. Embedded within this dust were compounds that Earth had not seen in its atmosphere since its own violent formation. Nickel, iron, complex silicates, rare trace metals fused in ancient stars. These particulates reacted with atmospheric moisture to form acidic compounds. When clouds condensed enough to produce precipitation rare, Under the dim, cooling skies, the rain that fell was not ordinary water, but a corrosive mixture capable of burning foliage, eroding soil nutrients and poisoning surface waters. Acid rain swept across continents in waves. Freshwater lakes turned toxic. Rivers carried death downstream, depositing chemical residue that suffocated fish populations and disrupted entire food webs. Amphibians already sensitive to environmental changes were among the first to disappear. Their extinction cascaded down lines of predation and ecological balance. Even the soil suffered. Nutrient cycles collapsed. Microbial life, normally resilient, struggled in the altered chemistry. Fungal networks withered. The great web of decomposers that Earth depended upon began to fail, leaving fallen trees, dead animals, and unprocessed organic matter accumulating in stagnant layers. The forest floor became a graveyard frozen beneath ash. Yet the oceans faced an even more harrowing fate. The shock of the impact had already generated immense tsunami waves and boiled coastal regions, but the true devastation occurred beneath the surface. Without sunlight, phytoplankton, the foundation of marine ecosystems, died off rapidly. Their collapse triggered a domino effect across the entire oceanic food chain. Zooplankton starved, small fish vanished, predatory species followed. Marine mammals, unable to find food, succumbed to starvation or cold. Oxygen levels in the oceans plummeted. Vast dead zones spread outward like wounds. In some regions, decomposition released methane and hydrogen sulfide, further destabilizing the atmosphere. The seas, once Earth's stabilizing cradle of biodiversity, became silent. The atmosphere changed more profoundly with each passing month. With plant life in retreat and marine photosynthesis halted, oxygen production dwindled. Carbon dioxide levels oscillated unpredictably, initially falling due to the light-blocking dust, then rising again as fires burned in smouldering remnants around the globe. Methane released from dying wetlands and melting permafrost in frigid climates to the mix, creating a chemical imbalance that outpaced any natural recovery mechanism. Above these changes, the destruction of the ozone layer began to reveal its consequences. With the upper atmosphere torn by the initial heat pulse and altered by metallic aerosols, the protective shield that once filtered ultraviolet radiation lay in tatters. Had sunlight returned earlier, it would have scorched the surface with lethal UV exposure, but the darkness lingered, masking this secondary danger, only delaying the inevitable. Life adapted where it could. Burrowing species survived longer than surface dwellers. Microbial colonies deep underground persisted in geothermal niches. Some fish retreated to abyssal depths where faint thermal vents still offered warmth. But these were pockets, not havens. The planet's biosphere was not merely wounded, it was fundamentally unbalanced, unable to sustain the interdependent cycles upon which life depended. Humanity's struggle grew increasingly desperate. Agriculture failed completely. The cold prevented germination. The darkness prevented growth. Greenhouses collapsed under ash layers, their artificial lighting insufficient against global shortages of energy. Livestock perished without feed. Fisheries collapsed. Water sources grew acidified. Even filtration and desalination systems faltered as chemical contaminants overwhelmed their capacity. Starvation became global. Some communities attempted hydroponics deep underground, but resources were limited. Others rationed dwindling reserves. Nations with larger stockpiles survived only marginally longer. Political boundaries dissolved. Cooperation frayed. Humanity, once united by shared vulnerability, fractured in the vacuum left by failing systems. Yet the planet itself kept changing. Volcanic activity surged Earth's crust, shaken by the impact's seismic shock, responded with eruptions around existing fault lines. These eruptions injected even more particulates into the atmosphere, prolonging the darkness. Earth, as if echoing the violence of Atlas, entered a self-reinforcing loop of cooling, darkening, and destabilization. The surface became a world of cold wind and ash. Ice surged across continents, forming sheets in places that had not seen frost in millennia. Glaciers formed rapidly. Rivers froze solid. Entire ecosystems disappeared beneath advancing cold. Where forests once stood, plains of ice stretched into the distance. Where grasslands flourished, only lifeless tundra remained. This was more than an impact winter. It was a planetary reset. Even after months of darkness, the world remained locked in a state from which recovery seemed almost unimaginable. The Earth had experienced mass extinctions before Chicxulub, the Permian collapse, the great anoxic oceans of earlier epochs, but Atlas produced a combination of chemical, environmental, and climatic upheavals unparalleled in the fossil record. It It was an extinction event without refuge, without a safe hemisphere, without cycles resilient enough to rebound quickly. And as the world sank deeper into this cold, poisoned quiet, one question overshadowed all others. If the night eventually lifted, would anything remain to see the dawn? As the world lay smothered beneath the pall of impact winter, a strange paradox unfolded in the silence. The darkness, the cold, the ash-filled skies all seemed immutable, as though Earth had entered a timeless twilight where light would never return. But deep within the atmosphere, beyond the reach of human eyes, a slow alchemy was taking place. The dust that had sealed the heavens was beginning particle by particle to settle. Gravity tugged at the suspended veil. Precipitation, faint and acidic, drew particulates downward. And as the atmosphere thinned, the first atoms of sunlight pierced the gloom. It was not a sunrise, more a trembling, a hesitant scattering of photons filtering through the clouds in scattered shafts. The light was weak, the warmth non-existent, but the long night had begun its slow retreat. This return of sunlight, however, was no salvation. It was the beginning of the second catastrophe. The dust veil, while catastrophic in its own right, had served as a temporary shield. It kept temperatures low, it muted chemical reactions driven by solar energy, and it prevented the vast quantities of greenhouse gases released by Atlas's vaporized carbon dioxide ice from taking hold. But Atlas was no ordinary comet. Its nucleus had been rich in frozen CO2, trapped for billions of years in its ancient interior. When the comet struck Earth, much of this ice vaporized instantly. The atmosphere absorbed it like a sponge. Carbon dioxide levels soared. Yet during the long winter, with sunlight blocked by dust, the planet's temperature fell despite the greenhouse gas spike. The dust veil suppressed heat, it reflected sunlight, it muted climatic feedback loops. But as the dust settled, the greenhouse gases remained. The slow reappearance of light did not bring warmth. It brought instability. Temperatures, still frigid, began to rise unevenly. Regions blanketed in ice remained frozen, while areas nearer the equator experienced sudden thaws. Permafrost artificially expanded by the impact, winter began to melt at its fringes. Methane, an even more potent greenhouse gas, escaped into the atmosphere in invisible torrents. The planet lurched from global cooling toward global heating. This transition was not smooth, it was violent. The atmosphere, still chemically altered by metallic aerosols and acid reactions, struggled to process the sudden influx of infrared absorption. The result was a climactic whiplash, rapid, unpredictable warming layered atop lingering cold. Storm systems formed in the vacuum between extremes. Superstorms fueled by the collision of warm air masses and frigid polar winds ripped across continents. Tornado clusters danced over barren plains. Lightning ignited surviving forests in bursts of electrical fury. Oceans responded with equal volatility. As sunlight penetrated the upper layers again, thermal stratification returned abruptly. Cold oxygen-poor surface waters warmed rapidly. Convection currents reactivated but stumbled in disequilibrium. Vast swathes of ocean turned anoxic. Hydrogen sulfide released by anaerobic bacteria thriving in this chemical chaos began to seep from the depths in poisonous waves. Marine life, already decimated, faced extinction across entire species lines, and still the warming intensified. The carbon dioxide from Atlas's vaporized ices represented only part of the greenhouse surge. Much of Earth's own carbon, sequestered for millions of years in biomass soils and marine sediments, had been released as fires ravaged the planet in the immediate days after impact. As surviving plant matter decomposed under abnormal chemical conditions, further CO2 and methane filled the air. With photosynthesis crippled, there was no mechanism left to absorb these gases. The atmosphere became a chamber of accumulating heat. Then, as the dust veil finally thinned to transparency, the full radiance of the sun returned. But the earth beneath it had changed. Instead of rich vegetation, darkened ash and exposed rock absorbed solar radiation with brutal efficiency. The planet's albedo, the reflectivity of its surface, had collapsed. Where forests once reflected and diffused sunlight, charred soil drank it in. Where ice once bounced heat back into space, melting glaciers exposed bare ground. Every shift accelerated warming. The planet's climate began to swing past equilibrium into an unfamiliar regime. Heatwaves struck regions still recovering from deep cold. Wildfires erupted in thawing tundra. Rivers swelled with sudden glacier melt, then vanished as evaporative losses accelerated. Lakes dried into cracked basins. Winds strengthened into continent-spanning tempests, sculpting dunes of ash where grasslands once flourished. This warming did not produce the vibrant ecological rebound that followed other extinction events. The biosphere was too broken. food chains too damaged, biological diversity too gutted. In past recoveries, sunlight returning after mass extinction had sparked bursts of evolutionary renewal. But now the timing was wrong, the survivors too few, the environment too unstable. The return of light became a threat rather than a blessing. As temperatures continued to climb, a third phenomenon appeared, one predicted by climate simulations but never witnessed in recorded human history: runaway evaporation. Bodies of water warmed far beyond their natural thresholds began to vaporize rapidly. Humidity spiked, clouds thickened, rainfall became extreme and unpredictable. Some regions experienced deluges that reshaped landscapes in days. Others remained trapped in cycles of drought and heat. The planet oscillated violently, unable to find balance. Behind every shift was the legacy of Atlas, the carbon dioxide ice locked in its ancient body now released into Earth's atmosphere. The comet's unique composition had not only triggered an impact winter, but had planted the seeds of a hypothermal future. This double catastrophe, first cold then heat, created conditions in which long-term survival became nearly impossible for complex organisms. The very systems that sustained life were in competition, warming, fought cooling toxicity, battled decomposition storms, clashed with droughts. Earth's climate had become a battlefield of feedback loops with no victor. Humanity, reduced to scattered pockets of survivors, experienced this transition with dread. The underground shelters that had protected them from the ash-choked winter now overheated. Food sources that had barely survived the cold withered under rising temperatures. Water once frozen solid became contaminated or evaporated. Technology, struggling under the combined weight of dust damage and power failure, faltered. For many, the warming proved more deadly than the cold. The planet once again was changing faster than its inhabitants could adapt. And as the heat rose, another silence overtook the world. Not the cold, brittle quiet of impact winter, but a heavy, suffocating stillness born of exhaustion, collapse, and the unravelling of the last remaining ecosystems. The long night had ended, but the long heat had begun, long before it became a threat, long before it ignited fear across continents or awakened ancient forces within Earth's atmosphere. Atlas was simply a question, a cosmic riddle drifting through the dark. It did not announce its origins, it offered no clear narrative of its birth. It carried only fragments of memory written in metal ice and interstellar dust. And once the immediate violence of the impact had passed, once the fires had burned out and the skies had turned opaque, scientists, or whatever remained of them, turned inward toward that original question, compelled to understand what Atlas truly was. Even in catastrophe, the universe had left behind clues. The first attempts to explain Atlas's existence began long before its descent toward Earth. These efforts emerged from astrophysicists, cosmochemists, and planetary scientists who saw in its metallic signature a history older than the solar system. But after the comet's catastrophic encounter with Earth, the need to understand became existential. Understanding Atlas meant understanding the mechanisms by which interstellar giants formed, wandered, and eventually intersected with young, fragile worlds like our own. The leading theories surrounding Atlas's origins fell into several intertwined categories, each illuminating different facets of the object's ancient identity. The first theory centered on stellar archaeology, the study of chemical signatures preserved in ancient bodies. Atlas's elevated nickel and iron content hinted that it formed in a region of the galaxy shaped primarily by violent stellar events, including supernovae. In such environments, newly forged metals were blasted into surrounding gas clouds, mixing with frozen volatiles before planet formation could stabilize the region. This suggested that Atlas was not merely old, it was primordial, a shard from a cosmic epoch when the galaxy itself was still churning with creative brutality. In this view, Atlas might have once been part of a larger proto-world torn apart before it could fully form its fragments, cast into interstellar space by gravitational upheavals surrounding unstable early stars. Another theory focused on galactic dynamics. In the Milky Way's thick disk, stars orbit with greater velocity and more erratic paths than those in the thin disk where the Sun resides. Encounters between stars or molecular clouds and early planetary debris were far more common. A single close stellar pass could have dislodged Atlas from its parent system billions of years ago, setting it adrift on a hyperbolic trajectory that eventually intersected the solar system purely by chance. Simulations suggested that thousands, perhaps millions of such objects wander the galaxy at any given time. Most pass unnoticed. A few become astronomically significant, but a vanishingly small number ever approach a populated world. Atlas in this interpretation was simply the unlucky messenger. A separate theory considered the object's internal structure. The high density of certain metallic inclusions suggested the possibility of layered formation analogous to the differentiation of planetary embryos. If Atlas had once been part of a molten or partially molten larger body, its metals would have migrated inward before being torn apart by gravitational forces. This implied a dramatic past catastrophic collisions, tidal disruption, or gravitational capture events. Perhaps Atlas was once a fragment of a shattered super-Earth or the remnant of a core stripped from a forming planet during a violent stellar encounter. The idea of planetary remnants wandering between stars was not new, but Atlas offered the first direct evidence a survivor carrying materials forged under pressures and temperatures not found in comets originating from the solar system. Some scientists even speculated about cosmic mixing, the idea that Atlas might have incorporated materials from more than one star. In regions where stellar nurseries overlap, interstellar gas clouds can intermingle, allowing fragments of matter from multiple stellar generations to fuse into new bodies. This would explain the comet's unusual chemical combinations, a mixture of young and old material, primordial dust and supernova metals, volatile ices and hardened regolith. But perhaps the most intriguing line of speculation concerned dark influences, the gravitational footprints of invisible structures. If Atlas had wandered for billions of years, it would have passed through regions dominated by dark matter filaments where gravitational forces behave strangely. These regions could have altered its path subtly, over immense timescales, nudging it through the galaxy in ways classical mechanics alone could not fully predict. Some researchers imagined Atlas as a test particle, its motion revealing unseen structures in the galaxy's gravitational landscape. In this sense, the comet was more than an object. It was a probe of the universe's hidden architecture. Others considered cosmic tides. The Milky Way, constantly evolving, pulls and stretches the orbits of stars and their debris. Massive objects, black holes, stellar clusters, galactic arms exert forces over billions of years. A comet like Atlas might have begun its journey in one spiral arm before being flung across another. Its hyperbolic velocity was not just a sign of interstellar origin, but of long-term gravitational interactions shaping and reshaping its path. Each theory painted Atlas not as an intruder, but as a participant in a vast cosmic story, one that preceded humanity by billions of years and would continue long after. And underlying all these theories was a final, more sobering question, one that blurred the line between astrophysics and existential reflection. Was Atlas rare, or was humanity merely fortunate to have avoided such visitors until now? Interstellar debris has always existed, drifting silently across the galaxy. But the detection of Oumuamua Borisov and now Atlas suggested that these objects were far more abundant than once believed. Most would never collide with Earth, but some, given enough time and enough wandering, inevitably would. The cosmos in its enormity does not observe boundaries. It does not separate stars from one another with walls or shields. Worlds form, drift, die, and are replaced. And between them, debris older than planets follows gravitational currents that flow for billions of years. Atlas was not an anomaly. It was a representative, a single ambassador of a vast interstellar population. Understanding its origins was not merely a matter of curiosity, it was preparation. The galaxy was not built for safety, it was built for motion, entropy, and change. Atlas simply fulfilled the natural consequence of that design. Humanity had always watched the sky for patterns, constellations, eclipses, predictable cycles, but Atlas revealed something darker. The sky holds not only patterns but probabilities, and some probabilities carry the momentum of worlds. Theories and speculations, in the end, could only answer so much. The deeper truth was simpler, more ancient, and more profound. Atlas was a fragment of a story older than Earth, and that story, written in the language of gravity and chance, had finally intersected with our own. Even as Earth's climate staggered between freezing collapse and blistering resurgence, even as ecosystems unraveled and civilizations dissolved into scattered enclaves, a quieter struggle persisted beyond the planet's surface. Humanity, reduced, fragmented, but not extinguished, continued to look upward. Across ruined observatories underground, research bunkers, orbital platforms still clinging to functionality. One shared task remained: understanding the visitors from the void and preparing for the next. Atlas had shown that the galaxy was not empty. It was full of wanderers, ancient shards, planetary remnants, interstellar comets forged in star-forming furnaces older than Earth. If one had struck so devastatingly, others could pass through again. And somewhere among the remnants of scientific society, a fragile determination took hold. They would not be caught blind a second time. Even before the final collapse of global infrastructure agencies around the world had rallied to build new detection systems, these were not the familiar planetary defense networks designed to track asteroids bound by the sun's gravity. These were instruments tuned to the unpredictable, to objects moving at interstellar velocities arriving from arbitrary directions, accelerating unpredictably due to internal forces. The first among these was the Interstellar Early Warning Array, a network of telescopes positioned at high altitudes and in deep dust-free deserts. Using cutting-edge photometric sensors, the array scanned for faint incoming objects whose trajectories broke the rules of local celestial mechanics. A typical near-Earth asteroid announces itself with detectable curvature as it responds to the sun, but interstellar visitors remain straight-line travelers until the very last moments. Their paths are lines, not arcs, and these lines must be caught early. Complementing ground-based systems, humanity accelerated the development of Deep Space Sentinel probes, autonomous craft placed in distant solar orbits, some stationed near Jupiter's Lagrange points, others drifting far beyond Neptune. These probes were designed to detect anomalies in background, starlight's subtle shifts caused when objects move too quickly or too silently to reflect sunlight. These probes listened to the dark not for light, but for absence of light, for the silent signatures of wandering bodies passing between stars. In orbit, the surviving fragments of space agencies launched a new class of sensor satellites built hastily from remaining resources. Their purpose was singular detect thermal signatures and anomalous motion at the fringes of the heliosphere. These satellites carried wide-field infrared detectors capable of noticing the faintest glow of sublimating ice tens of millions of kilometers away. They scanned relentlessly, powered by the last functioning solar arrays in low Earth orbit. But perhaps the most important efforts emerged not near Earth but far beyond it. Before the collapse of global industry, humanity had launched a fleet of long-range deep space telescopes positioned in solar orbit at vast distances. Their instruments were dedicated to surveying interstellar space itself, not the planets, not the asteroids, but the galaxy beyond. These telescopes examined the movements of faint objects moving against the dense starfields of the Milky Way. They captured the signatures of bodies whose velocities exceeded solar escape speed. Each detection added to a growing catalogue, a map of wanderers that had passed near the sun long before humans ever looked up. From this archive, scientists began to understand something profound. Interstellar objects were not rare exceptions, they were constant. A steady rain of cosmic debris drifted through the space between stars. Most were small dust-like, harmless. A few were mountains of ancient ice and iron. Atlas had been one of these, and there would be others. Even in devastation, astronomers continued developing technologies to decode these visitors. Spectroscopic sensors were enhanced to detect exotic isotopes unique to thick disk stars. Artificial intelligence systems processed petabytes of sky data, filtering noise to find faint anomalies that once would have been dismissed as instrumental error. Machine learning models learned the signatures of interstellar drift, linear motion, extreme velocity, erratic brightness, curves caused by ancient tumbling rotation. But Earth's position as a scientific hub had weakened. Many researchers turned to the moon or orbital habitats where sunlight had returned earlier and environmental conditions were more stable. Telescopes were erected on lunar highlands sheltered beneath thin atmospheres of dust free from Earth's aerosols. These instruments provided unparalleled clarity. They became humanity's last eyes on the cosmos. From this vantage, scientists observed evidence of other interstellar objects passing through the solar system during the long global winter. None approached as closely as Atlas had. None carried comparable mass or destructive potential. But each arrival rekindled the knowledge that the universe remained full of ancient wanderers and that Earth had simply been struck by one of the rare giants. Studies deepened. Astrochemists examined microscopic remnants of Atlas that had fallen back to Earth, tiny beads of molten glass, metallic droplets cooled in the stratosphere. These contained isotopes from ancient supernovae, rare crystalline structures, formed in environments of extreme radiation and compounds unknown in any terrestrial context. The samples revealed secrets older than the sun messages encoded in the material memory of a fragment forged when the galaxy was young. Theories emerged, some bold, some unsettling. Perhaps interstellar comets like Atlas played a fundamental role in distributing the raw materials of life across the galaxy. Perhaps they seeded worlds with carbon, nitrogen, and water. Perhaps some carried more than chemistry, perhaps they carried biological precursors or even macromolecules resilient enough to survive cosmic travel. These ideas were not new, But Atlas provided the first physically indisputable proof that interstellar bodies could deliver complex chemistry across star systems. Cosmologists considered a deeper possibility that the galaxy's thick disk with its ancient stars and violent origins was a crucible for life-bearing chemistry on a scale the solar system could never match. And yet even as scientific revelations deepened, another truth grew impossible to ignore. For all its wonders, all its secrets, Atlas had delivered devastation. The universe gives and takes without preference. It offers life to some worlds and extinction to others. It is without malice, without benevolence, only motion, energy, and chance. Humanity's telescopes, probes, and observatories became something more than tools. They became shields, not physical ones. Earth could never deflect an object as massive as Atlas, but intellectual shields meant to provide early warning, preparation, understanding. Because survival humanity now knew depended not on strength, but on foresight. Eyes in the void had become essential to the future. Atlas had shown why. In the final reckoning, when the ashes had settled and the echoes of impact had faded into geological memory, the universe remained unchanged in its vast indifference, but humanity, or what little remained of it, had changed irreversibly. The catastrophe wrought by Atlas had revealed something deeper than destruction. It exposed the fragile boundary between existence and oblivion, the thin thread of probability that allowed life to arise on a small blue world orbiting an ordinary star. Long after the fires cooled, long after the long night passed into the long heat, and long after the oceans and skies transformed into unfamiliar versions of themselves, the memory of Atlas persisted not as fear, but as a kind of cosmic truth. A truth written not in scripture or story, but in physics, time, and the silent trajectories of ancient wanderers. The universe is not a quiet place. It is restless, filled with motion and remnants. Comets older than worlds drift between stars like seeds scattered across a boundless plain. Some bring life, some bring ruin. Most pass unseen, slipping through the dark with no witness, no record, no memory. Atlas was not the first such traveller. It would not be the last. But it was the one that intersected Earth at exactly the wrong moment. When astronomers, survivors of the collapsing world, studied the historical projections of Atlas's path, they found an irony that bordered on poetic. For millions of years, the comet had passed close to countless stars. It had skimmed the edges of unknown planetary systems. It had drifted near worlds that may have harboured life or worlds that never knew it. Its trajectory had been sculpted by gravitational fields altered by passing stars nudged by invisible clouds of interstellar dust. Any slight change, any nudge a billion years earlier could have diverted it by entire astronomical units. It might have passed silently beyond the reach of the sun. It might have slipped through the outer solar system unnoticed. It might have crossed Earth's orbit centuries before humans existed, or millennia after they vanished. It might have brushed a different planet, or none at all. But the cosmos did not plan, nor did it choose. It simply allowed. Atlas arrived not by intention, but by the impartial arithmetic of celestial mechanics. Gravity guided it, heat shaped it, chance defined it. And Earth, in its improbable vibrancy, found itself standing in the path of a relic from another epoch of the galaxy. Scientists piecing together its final structure realized that Atlas was more than an interstellar comet. It was a mosaic of cosmic history, a fragment of the thick disk, a remnant of a star-forming region older than the sun, a traveller forged in environments Earth had never known and would never see. What struck the planet was not merely a comet, it was a messenger from the galaxy's ancient childhood. If the universe had a memory, Atlas was part of it, and in striking Earth it left behind a new chapter in that memory, a chapter written in atmospheric scars and geological layers, in the stories of survivors and the silence left behind by those who did not endure. Earth had weathered extinctions before. It would weather this one too slowly, painfully through cycles of heat and rebirth. Life in 10,000 or 100,000 years would begin its fragile climb again. Microbes would reclaim the seas, hardy plants would anchor themselves in the shattered soils, animals small and desperate would adapt or perish. Evolution would continue, sculpting new forms, weaving new ecosystems from the ruins of the old. And deep within the sedimentary layers, future beings, whatever shape they might take, would find the imprint of an event unlike any other. A thin band of ash containing exotic isotopes and ancient metals, the signature of a traveller from beyond the sun. In this way, Atlas became eternal, not in its physical form, which disintegrated in an instant, but in the story it left behind, a story that outlasted the species that witnessed it. For even in devastation there is knowledge, even in erasure there is memory, and even in extinction there is continuation. Earth would go on, the universe would go on, the stars would continue their slow orbits around the galactic centre. Other comets would drift, Other worlds would rise and fall, and somewhere perhaps in a distant system orbiting a distant sun, another civilization might one day look outward and wonder about the wanderers in the dark. The same question would echo there as it did here. What ancient strees crossed the void unannounced, unseen, until the moment they arrived? Atlas had been one such story. Its beginning lay in forgotten stars, its middle unfolded in the cold between suns, and its end, violent, transformative, unforgettable, was written upon Earth. It was a reminder that no world exists alone, that the cosmos is a single restless ocean, that even the smallest traveller hardened by time and distance can shape the destiny of a planet, and that every world, no matter how bright, is only ever one collision away from silence. And now, with the final echoes of Atlas settling like distant thunder across the memory of a changed world, the narration softens, the pace eases, the imagery quiets. The universe once roaring with fire and shadow dims into a calmer, slower breath. Imagine for a moment the Earth long after this story ends. The skies have cleared, the oceans reshaped by cold and heat alike rest under gentler winds. The last remnants of ash have become part of the soil. Sunlight once lost behind a curtain of dust now moves freely again across empty plains and quiet seas. The air is thin, the world altered, but there is still motion, still warmth, still time. Somewhere in the deep where darkness never ends, small creatures drift in slow spirals, unaware of the history above them. On land, the first shoots of green rise cautiously from a fractured crust. They do not know fear. They do not know memory. They only grow because growth is what life remembers how to do. Above the constellations remain unchanged silent witnesses to the long recovery. They shine the way they always have, without urgency, without sorrow, without intent. The universe does not offer comfort, but neither does it deny it. It simply continues. And Earth, turning patiently beneath those indifferent stars, begins again. Not as it was, not as it will be, but as it is in this moment, quiet, altered, enduring. Across the cold breadth of space, the echoes of ancient wanderers drift onward. And here, on a planet that has seen both creation and collapse, the night slows, the winds soften, and the long, fragile story of life prepares to write its next chapter. Sweet dreams.